right. When we talk measurement, we're talking about, we sort of think inches, feet, yards. You might think metric, which would be centimeters, meters, liters, milliliters, those kinds of things. And we're certainly going to get there. But before we talk about those, before things got standardized, there were measurements used by ancient civilizations. And here's just sort of some examples of those. A foot would be kind of what you would think, the length of a foot before it got standardized. A span is the distance from the tip of your thumb to the tip of your finger when you widen your hand out as far as possible. A hand, which is still used to measure horses, is from one side of your palm to the other side of your thumb when it's pressed together that way. The yard, where it came from, was from the nose to the tip of the fingers. That distance is a yard. And then one that you'll see in some ancient references goes from elbow to the fingertips, and that is called a cubit. We're not going to do a whole lot with spans, hands, or cubits, but I did want you to know that these exist. These were measurements that were used for centuries before our measurements got standardized. You're probably pretty familiar with the standard English units that we use: inches, feet, yards, miles, ounces, pounds. So we're going to spend a little time talking about the metric units that you might not be as familiar with. When we're talking about length, the basic unit of measurement for length in the metric system is the meter. And a meter is approximately 1 yard. A little bit longer than a yard, but pretty close to a yard, just to sort of give you a visual way of thinking about a meter. And then we'll talk about these prefixes here in a few minutes, but for right now, when we look at a centimeter, that is a piece of a meter. A centimeter is less than 1 inch. And then a kilometer is bigger than a meter. And a kilometer is approximately 0.6 of a mile. So a little bit more than half a mile would be a kilometer, just to sort of give some relevance to those. Then we move on to volume, which is how much stuff could fit inside a container. Liquid measurement is most common for us with these, and a liter is the standard unit of measure in the metric system. And a liter is about 33 ounces, so it's a little bit more than a quart. We're pretty familiar with 2-liter bottles when we buy pop, so that's, a liter would be half of one of those. Another prefix for us to look at is milli, and a milliliter, there are 1,000 of those in a liter. So it's a very small measurement. Then we have weight, which is the standard unit, is the gram. And probably easier to have a frame of reference to instead of a gram. Oops, that should say kilogram right there. A kilogram is 2.2 pounds. So a kilogram is about 2 pounds. So, if you weigh 150 pounds, then you weigh somewhere in the neighborhood of 75 kilograms, because a kilogram is about 2.2 pounds. And then the gram is our standard unit, and a milligram is even smaller still. Let's talk about the prefixes that are on this page. We said that the meter was our standard unit for the metric system. So you see centi over here. Centi, like there's 100 years in a century. And so when we have a centimeter, there would be 100 of these in 1 meter. The prefix kilo goes with 1,000. Since the kilometer is bigger than the meter, then there would be 1,000 meters in 1 kilometer. And so kilo goes with 1,000, centi goes with 100. Smaller than the liter, milli also goes with 1,000. We couldn't call it a kiloliter because that would be bigger than a liter. So when it's smaller and the relationship is 1,000, we use milli. And so there would be 1,000 milliliters in 1 liter. And then down at the bottom, we kind of can see where these are headed. Gram is our standard unit. Milligram, again, the prefix milli goes with 1,000. So we would have 1,000 milligrams in 1 gram. And then kilo also goes with 1,000. So there would be 1,000 grams in 1 kilogram. These are sort of the main prefixes we use. We're going to look at prefixes again here in just a second, but these are some of the primary prefixes that we do use. Make sure to let me know if you have questions as we talk through them. Here's sort of a chart that puts it all in place for us. We can see the base units of meter, gram, and liter. And we can see how if we have a millimeter, that it would be 1/1000th of a meter, or it would take 1,000 milliliters to make 1 meter. And that works the same with the other units also. If we had a milligram, it would take 1,000 milligrams to make 1 gram, and 1,000 milliliters to make 1 liter. Most commonly with meters, we'll use centi. We'll see centimeters. A centimeter is 1/100th of a meter. So it would take 100 centimeters to make 1 meter. We don't see centiliter or centigram very often. Really, centi is primarily used with meter. Deci is 1/10. While that one's true, it's not one that we use very often. The same thing applies to deca, which would be 10 meters would be a decameter, but again, that's not one that gets used very often. Hecto would be 100. Again, not one that's used very often. Much more common for practical purposes is the prefix kilo, which relates to 1,000. And we'll have kilometers, kilograms. Kiloliters would be something awfully big, but again, kilo, milli, and centi are the ones we're primarily concerned with. Let me know if you have questions. The next thing I want to talk about is sort of relative sizes, just to sort of ballpark it. And, I talked about how a meter was a little bit bigger than a yard, and that, a liter was a little bit more than a quart. But these are some real life things that give us another way of thinking of these. So like the width of a doorway, that's about 1 meter. So if you need to visualize how big is a meter, the width of a doorway is a good sort of reference point. The height of an average man would be about 1.77 meters, but honestly, I think in countries that use the metric system, it's more common to represent height in centimeters than it would be in meters. The mass or weight of an average hardback textbook is about 1 kilogram, about 2 pounds. So that's in the ballpark. The weight of a relatively thin adult could be 60 kilograms. That would be roughly 125 pounds. I'm going to jump down to the bottom real quick here and talk coffee cup. How much liquid can fit inside a coffee cup? Well, that's about 250 milliliters, or about 1/4 of a liter. Just to give you some references for how big or small these things are if you're not really familiar with the metric system. The two that I skipped over were about temperature. And with temperature, we use the Fahrenheit system. And in metric, they use the Celsius system. We'll talk a little bit more about that in just a minute. But in the Celsius system, a warm day would be in the neighborhood of 27 degrees Celsius. If it's a cold, wintry, snowy day, now you're talking about -4 degrees Celsius. So Celsius numbers are going to be very different from ours, especially on the warm day. That 27 degrees would be a warm day, a little bit different than our Fahrenheit system. Let me know if you have any questions that come up. We'll talk a little bit more about those temperatures. Celsius and Fahrenheit. In our Fahrenheit system, water freezes at 32 degrees and it boils at 212. So water freezes down here at 32 degrees. And, if we kind of have our little thermometer over here and it goes all the way up to 212, that's where it boils. In the Celsius system, and if you know a little bit about the metric system, it's based on tens and hundreds and thousands. And so in the metric system, using Celsius, water freezes at 0 and boils at 100. So it freezes at 0 and it boils at 100. So we can kind of see some parallels there. In the Celsius system, a temperature of 0 degrees would correspond to 32 degrees Fahrenheit. In the Celsius system, 100 degrees would correspond to 212 degrees Fahrenheit. So we definitely wouldn't have any 100-degree days when we're talking about weather in the Celsius system. If we want to go back and forth between these two systems, between Celsius and Fahrenheit, the relationship can be found in this formula right here. The Fahrenheit temperature is equal to 9/5 times the Celsius temperature plus 32. An example of that. If it's 18 degrees Celsius, what would the temperature be in Fahrenheit? And we can take a look at that. So if it's 18 degrees Celsius, what would the temperature be in Fahrenheit? We're going to use this formula right here. And the Fahrenheit temperature would be 9/5 times the Celsius temperature, which we were given as 18 degrees, plus 32. We have to remember order of operations here. We're going to multiply first, and then we're going to do the addition. So we're going to multiply, then we're going to add. So to multiply these, let's see, it's a fraction times a whole number. I'm going to rewrite that whole number as a fraction. Now I can multiply. Now I'll have 9 times 18. I don't know what that is. 9 times 18 is 0.5. Wait. How about 9 times 18? There we go. 162. So 162 over 5 times 1 is 5 plus 32. We're going to be okay with a decimal answer here, so we can go ahead and do the 162 divided by 5 and get 32.4. We'll add 32, and we'll end up with 64.4 degrees. So if it's 18 degrees Celsius, that would be 64.4 degrees Fahrenheit. And we just use the formula to convert. We were given the Celsius, we found the Fahrenheit. Any questions on that before I have you try one that's similar? All right, here goes. If the temperature is 86 degrees Fahrenheit, what would it be in Celsius? And just as a reminder, I'll put that formula here for you. Fahrenheit is 9/5 times Celsius plus 32. I'll set up a poll for this one and let you try it. Find the temperature in Celsius if we know what the temperature is in Fahrenheit. I didn't say it round to the nearest tenth in the problem, but all the answers are rounded to the nearest tenth. So that's what we're going to do. You might see a question like this on a quiz or an exam, so it's a good thing to be able to do. Relatively straightforward formula, but I want to make sure that you're able to solve a question like this. We'll go another 30 seconds, and then we'll talk through this one. Let me know if you need more time. All right, let's see where we are on this one. Okay, pretty strong agreement. That's usually a good indicator. Let's go take a look at this one and see where we are. Okay, so what this question said is, if the temperature is 86 degrees Fahrenheit, what would it be in Celsius? So we've been given the Fahrenheit, and what we're trying to find is the Celsius. So what we're going to plug in for here is the Fahrenheit. We know that it's 86 degrees Fahrenheit, and what we're after is what Celsius temperature would go with that. Unlike the last one where we just had to plug it in and simplify, this time we actually have to solve an equation. We haven't done much algebra in a while, but remember, whenever we are solving an equation, we're trying to get this c by itself. So we need to get the term that has c by itself. So on this right-hand side, we're going to peel this onion from the outside in. The first thing we're going to get rid of is that 32. So we're going to subtract 32 from both sides. We'll subtract 32 on the right and the left. On the right, they cancel, leaving me just 9/5 times c. And on the left, I have 86 minus 32, or 54. Okay, now I have to get that c by itself, which means I need to get rid of 5/9. In order to get rid of that 5/9, what I need to do is multiply by the reciprocal. I'm going to multiply, or excuse me, to get rid of 9/5, I'm going to multiply by 5/9 on the right. I'm also going to multiply by 5/9 on the left. On the right-hand side, the 5s cancel, the 9s cancel, and all we have left is the c. That was our goal. That was what we were trying to accomplish there. On the left-hand side, I have 54 times 5/9. And in order to do that, we can start by multiplying 54 times 5. And now I've got 270 over 9 is equal to c. Let me back up 1 second here. We're multiplying those fractions together, so I can rewrite 54 as 54 over 1. I'll multiply numerators. 54 times 5, that's where the 270 comes from. Multiply denominators, 1 times 9, that's where that 9 comes from. So that's how we end up with 270 over 9. Last thing we'll need to do is just divide those, and 270 divided by 9 is 30. So if the temperature is 86 degrees Fahrenheit, then it would be 30 degrees Celsius. We had a rare occurrence there where we had strong agreement, but not the correct answer. So if you don't see why your answer was the wrong one, make sure you ask about it. And I will say in the previous question, we were given Celsius and asked to find Fahrenheit. In this one, we were given Fahrenheit and asked to find Celsius. Well, we can talk about that, Stephanie. Let me know what you did. Let's talk through it. It's kind of fun to see if an alternate method results in a correct answer. Hmm. Okay. I'm skeptical at this point. Okay. And that would be a way to find if we were given Fahrenheit or if we were given Celsius and we were looking for Fahrenheit, those would be the right steps. But keep in mind, our correct answer here was 30 because we weren't given Celsius to find Fahrenheit. We were given Fahrenheit and had to find Celsius. What you did was the right thing if we were given Celsius and we were looking for Fahrenheit. But here we were given Fahrenheit and we were looking for Celsius. Okay, perfect. Very good. Very good. Right, Escadar. That's the same thing that Stephanie did there. Um, in the first example, we were given Celsius and asked to find Fahrenheit. And so our process was to plug in and simplify. But this question was different from that. This question used the same formula, but this time we were given Fahrenheit and asked to find Celsius. So since we had a different thing that we were asked for, we had to use a different process to get there. All right, very good. Perfect. Perfect. A lot of people really like the metric system because it's based on tens and ones. When it was becoming popular, there was a time where the French Academy of Sciences said that we should try using the metric system for time. And what they proposed was that there would be 10 hours in a day, 10 hours in, or excuse me, 10 days in a week, and 10 months in a year. And so while this sounds kind of nice, 10 hours in a day, so an hour would have to be about 2.5 times as long as it is now for that to work. 10 days in a week, I'm not sure exactly how you're going to pull that off other than, now a week is 10 times that, that the sun rises and sets instead of 7. And then the 10 months in a year, a month would have to be longer to still accommodate 365 days. So while a lot of people like things about the metric system, time did not get accepted, this did not get approved, and did not get put into place. Kind of curious though, kind of interesting to think about that the way we measure time is totally up to us. It's not, this isn't something like gravity that was here before people. The way we measure time is totally up to us. Accuracy and precision are two different things that often get confused with each other. And so we're going to talk about the definitions of those, what they are. Accuracy is how close is the measurement to the true measurement? Is it accurate? Is it close to the real thing? Precision, however, is really more about the tool that you're working with. How exact is your measurement? So accuracy is it right? Precision is how detailed can you really get? How good is your measuring tool? An example of these would be if you said that my height was 48.3165 inches. That's very precise. I mean, it goes all the way to the 10,000ths place. The problem is I'm nowhere close to 48 inches tall being correct. So this is not accurate. I'm not 4 feet tall. So while this is very precise, it's not accurate. And then the other way around, you could say that I was 6 feet tall. Well, this would be relatively accurate. I'm pretty close to 6 feet tall. That's pretty close to the actual truth. But it's not very precise because you just kind of ballparked it, went with 6 feet. You know, if you said 5 feet 10 inches, now you're more precise. If you said 5 feet and 10.127 inches, now you're accurate and precise. In these, and so the distinction between being accurate and precise is one that I may want to make sure you're aware of. Accurate means your measurement is close to the truth. Precise really has to do more with your measuring tool. How exact did you go with your measurements? Ideally, we get both. Sometimes we get one but not the other, and that's what these two examples are about. So how accurate is a measurement anyway? That's what percent error is about. And percent error is found using a formula. And it's the amount of error divided by the actual amount. So we can calculate the percent error for a given situation and know how accurate a measurement really is. Percent error is a way for us to do that. On the next page, we're going to look at a question that comes up, and I'm going to do the first one and then have you do the second one so that you can answer the question. Here's what I mean. A 6-foot tall man is measured to be 10 feet tall. A 76-foot tall building is measured to be 80 feet tall. Which of these has a higher percent error? The man or the building? I'm going to do the man, then I'm going to let you do the building and let you answer the question. So first, when we're looking at the man here, so for the man, the percent error is going to be, well, let's see, the amount of error. So he was measured to be 10, but his actual height is 6. So we'll subtract to find the difference. That's the amount of error, the difference between the actual measurement and how much it was measured to be. And we'll divide that by the actual measurement. This is the key part here. It's the actual that goes on the bottom. So make sure you're careful with that. The actual goes on the bottom, and that's the 6. And so we subtract here, and we have 4 over 6, and we can divide that. 4 divided by 6 is, let's see, that's 0.66666, and that keeps repeating. This is written as a decimal. The concept is called percent error, so we want to write this answer as a percent. So we'll move our decimal place just 2 places over and see that this is 66 point, we'll go to the hundredths place, 67%. So the percent error for the man is 66.67%. What I want you to do is find the percent error for the measurement of the building and then answer the question, which has a higher percent error? I'm going to set up a poll for that. And what we're finding with the percent error here and comparing these two is we're finding, which one is less accurate, which one's off by more. That's what we're trying to find here. And percent error is how we'll make that determination. Which one's off by more? Which one's less accurate? The higher the percent error means the less accurate the measurement is. We'll go another 30 seconds. If you need more time, let me know. Let's take a look and see where we are. Not unanimous, but pretty close. Definitely strong agreement. Let's see what that tells us in this one. So keeping in mind that our idea here is the higher percent error means that the measurement is less accurate. So a higher percent error means it's less accurate. It's off by more. All right, let's take a look at our building. So for our building, our percent error will be, let's see, it was measured to be 80, but the actual height is 76, so it's off by 4. The difference between those will give us the amount of error in our numerator. And then in the bottom, we put the actual amount. The actual amount is the 76. That's how tall it is. And so let's see, for this one, we'll have 4 over 76. And we'll divide that. 4 over 76 is 0.05263. And it keeps going. We rounded the last one to the nearest hundredth after converting it to a decimal. So let's convert to a decimal here. We'll do that. We'll move a decimal over 2 places, and we'll have 5.26%. So the percent error for the man was 66.67%. The percent error for the building was 5.26%. So which of these had the highest percent error? Because this number is larger, the man had the higher percent error. The reason percent error is what tells us which one's less accurate is, I just kind of want to take a second and investigate a little bit. You know, if we look, well, the man was 6 feet tall, measured to be 10, so that's off by 4 feet. And the building was 76 feet tall and measured to be 80, so that's off by 4 feet. They're both off by 4 feet. It'd be easy to think, well, then it's the same. But if you just sort of take a step back and think about the context of this, if you measure a 6 foot tall man to be 10 feet tall, you're way off, because this 4 is the amount of error is really big compared to the actual amount. When we go look at the building, now we're saying, yeah, you're off by 4, but I mean, 76 feet, 80 feet, it's not off by that much given the context that we're working with. This difference of 4 is a lot less significant when we're talking about something that's 76 feet tall compared to talking about something that's 6 feet tall. And that's why we look at percent error to tell us how accurate something is. Not just the raw number, but okay, how far is it off from what it actually is? Because something that's not that big, this much error is a lot. Something that is bigger, this much error, okay, it's off by 5%. That's not great, but at least it's not off by 67%. You know, that's very far off of the actual measurement. All right, we've talked a little bit of metric. We did Celsius, Fahrenheit. we've done accuracy and precision, we've done percent error. There's one more big idea that we'll talk about, but before we get to that, I want to give you a chance to ask any questions on anything we've done so far. Okay, fantastic. Dimensional analysis. This is something that you may have seen before in especially a science class. If you took a chemistry class somewhere along the lines, you probably would have seen dimensional analysis. It's when we use what are called unit fractions to convert from one unit of measurement into another. So we're given some measurement that we need to convert to different units. The way we're going to do that is we're going to use what's called unit fractions. And here's some examples of those. The idea that there are 12 inches in 1 foot. The reason this is called a unit fraction is partially because we have this 1 down here. There's one of these. That's our unit of measurement, 1 unit. And also really important in unit fractions is that the top and the bottom of these are equal to each other. The top and bottom are equal to each other, 12 inches and 1 foot. Those are exactly the same. So we have the top and the bottom that are equal to each other. And anytime we have a fraction where the top and the bottom are equal to each other, that has a value of 1. And here, if it's 12 over 12, that has a value of 1. Anytime the top and bottom are equal to each other, the value of that fraction is 1. And that's what we've got here with 12 inches over 1 foot. A couple of other examples. We could say that there is 1 mile in 5,280 feet. Those two are the same as each other. 1 mile is 5,280 feet. They're the same. They have different units, but their value is identical. And then another example would be 1 inch is 2.54 centimeters. 12 inches and 1 foot is probably walk around common knowledge. 5,280 feet in 1 mile might be for some of you. And then going in from English to metric, the idea that 1 inch is the same as 2.54 centimeters, there's another unit fraction that we can use when we're making conversions. So these are examples of unit fractions that we're going to use when we convert units. We're going to look at some examples. I'm going to have you try it. This is a topic that sometimes gives students trouble, but we're going to practice it and work on it, and I'm confident you can master this. Let's take a look at one. A recipe calls for 250 milliliters of milk. How many liters is this? So something that's going to be really important for us to know in order to do this. We're trying to convert milliliters to liters, so we need to know that there are 1,000 milliliters in 1 liter. That's going to be the unit fraction that we use to do this conversion. Sometimes when we work on problems like this, students don't know where to start. I'm going to clear that up right away. You start with whatever you've been given. We've been given 250 milliliters of milk. So that's where I'm going to start, is with my 250 milliliters. You don't have to set up a scaffolding like this, but it is the most common way to do these, is to set up a scaffolding. And really all we're doing here is setting up a place to put the numerator and denominator of our fractions. We're going to put a numerator and a denominator over here. I've done these with students who are perfectly comfortable with the whole process and don't like the scaffolding. You don't have to use the scaffolding if you don't want to. It's really just there to help us stay organized. If you took a chemistry class and you see this and you immediately break into a cold sweat, maybe don't use the scaffolding because you don't have to. But I'll probably use it most of the time just to kind of show you that this is sort of the standard way that these are done. It's just a place for us to put the numerator and denominator of a fraction and to make sure we have something on top and something on the bottom. So the unit fraction I'm going to use here involves this fact right there, 1,000 milliliters to 1 liter. What I'm trying to do is Right now, I have milliliters. I don't want to have milliliters. I want to have liters. So when I use this fact over here to write my unit fraction down, what I'm going to do is I'm going to put the 1,000 milliliters on the bottom and the 1 liter on the top. The reason for that is because you could be thinking, well, what if I wanted to do it the other way? What if I wanted to put the 1,000 milliliters on top and the 1 liter on the bottom? The problem with that is it doesn't help us get to where we're trying to get to. Because this way, I've got milliliters on top and milliliters on top. Well, that's no good. I'm trying to get rid of milliliters. So what I want to do is I want to put those 1,000 milliliters on the bottom and the 1 liter on top. The reason for that, because I want milliliters to go away. And by having one on the top and one on the bottom, they'll cancel. Now, the only units I have left are liters. And that's exactly what I was trying to get to. I said, how many liters is this? So I've caused milliliters to cancel. I'm taking this thing that I was given, I'm multiplying by a fraction that's equal to 1, so it doesn't change the value at all. And now the only thing left for me to do, once I get my units squared away, is multiply what's on top, 250 times 1, so that'll be 250, and that liters comes along. And on the bottom, I don't have any units at all. All I have is that 1,000, so that goes down there. And the last thing I need to do is go ahead and divide those numbers to simplify this. 250 divided by 1,000. And I get 0.25. So the question said, a recipe calls for 250 milliliters of milk. How many liters is this? It's 0.25 liters. That is an extremely simple example of a dimensional analysis question, but this is the idea behind dimensional analysis. Really quickly, I'm going to do this without the scaffolding in case you don't want the scaffolding. It's not going to look any different as far as the numbers go. 250 milliliters of milk, and I want to know how many liters it is. I start with the 250 milliliters I was given. Instead of setting up a scaffolding, I know I'm going to be multiplying by some unit fraction. This fact over here gives me my unit fraction. I want the 1,000 milliliters on the bottom. I want the 1 liter on the top. Milliliters cancel. I'll multiply across the top and have 250. Multiply on the bottom. There's just one number down there is 1,000. That's how many liters I'm going to end up with. And it's exactly the same, 0.25 liters. If you don't like the scaffolding, you don't have to use it. I probably will. But if you don't use the scaffolding, it's just going to look a little different. It's just going to look like this thing multiplied by this fraction instead of the fraction being written on the scaffolding. Are there any questions about this one before we move on to something that is the same idea, but a little bit more involved? All right, great. Use the fact that 1 inch equals 2.54 centimeters. So right away I can see this is going to be a unit fraction that I'm going to use to convert 40 inches to meters. So what this problem wants me to do is I want to convert 40 inches to meters. I'm going to start with inches. I need to turn that into meters. All right. So I'll start this thing with whatever I was given, which is those 40 inches. All right. Now, I'm going to put a unit fraction over here that helps me move closer to meters. The one we looked at in the last problem was just one step. That's pretty rare. Typically, we're going to need more steps than that. So what I'm trying to do is not necessarily go all the way to meters in one step. I'm just trying to get myself on the road to meters. And one thing that I can see here, the thing that's going to take me from inches to centimeters is this unit fraction right here. 1 inch is 2.54 centimeters. So right here and right here, somewhere I'm putting 1 inch, somewhere I'm putting 2.54 centimeters. Am I going to put that 1 inch on the top or on the bottom? And you can just let me know by typing this one. I'm not going to do a poll for it. The 1 inch, does it go on the top or the bottom? Outstanding. Very good, everybody. That's great. This is the part that sometimes gives students trouble. It's really good to see that you're already pretty comfortable with it. The 1 inch is going to go on the bottom, and the 2.54 centimeters goes on the top. And that's not a guess at all. That is purposeful. I've got this inches up here on the top. In order to cancel inches and get inches to go away, I need to put inches on the bottom. And once I've done that, now my inches on the top cancel with my inches on the bottom. Okay, this problem told me to convert inches to meters. Well, I started with inches and now I have centimeters. So I'm not done yet, but I'm definitely on the road. So the next thing I'll need to use is a unit fraction that will convert centimeters to meters. That's what I need to do next. Well, let's see. Maybe it's metric system's a little new, but there are 100 centimeters in 1 meter. With that in mind, with 100 centimeters equaling 1 meter, I'm going to make that my next unit fraction, and I'm going to put one of those terms is going to go on top, one of those terms is going to go on the bottom. Which of those terms, centimeters or meters, is going to go on the top? Very good, Natalie. Great, excellent. I'm excited to see this. Sometimes these give students trouble. I get a sense that we're doing pretty well with this, and that's awesome. So I'm going to put that, and it's really where my focus goes is I need centimeters to go away, so I need to put 100 centimeters on the bottom. And then by default, the 1 meter goes on top. And once I've done that, now I've got centimeters on top, centimeters on the bottom, those cancel. And as I look at my units, okay, I started out with inches. I used this unit fraction here, and then I had centimeters. Now I've used this unit fraction here, and now I have meters. And the problem told me to convert to meters. So what that means is I'm done. I've done all the unit fractions I've needed to do because the units are where I want them to be. Now what I need to do is multiply everything on top. That's 40 times 2.54 is 101.6. And on the bottom, I have 1 times 100 or 100. And the only units I have left are meters. So this is how many meters I have. Last thing I'll do is divide by that 100, and I get 1.016 meters. This problem actually told me where to round the nearest thousandth, and that's where it is. So 40 inches would be 1.016 meters. And that's how we do a dimensional analysis question. This one had 2 steps. I had to use 2 unit fractions to get there, but that's the process. We use a unit fraction to get to the next step, and eventually the next step gets us to the answer we were looking for. Are there any questions about this before I have you try one? All right, here goes. Use the fact that 1 kilogram equals 2.2 pounds to convert 165 pounds to grams. And I'm going to throw you a bone here and let you know that 1 kilogram, or excuse me, 1 kilogram is 1,000 grams. All right. So with those facts in mind, maybe you didn't need that, but I figured I'd give it to you anyway for the sake of the poll. Convert 165 pounds to grams. I'll set up a poll for this, and I'll give you some time to try it. Don't have to be in a hurry on this one. As you work through this one, remember, start with 165 pounds, and then we need to eventually get that to where it's grams. We use unit fractions to change our units, and then once our units are grams, then we know we've done all the unit fractions we need to use. We can go 30 more seconds on this and then talk about it. You let me know if you need more time because we're in really good shape on time. All right, let's see where we are on this one. We're unanimous. That's good news. Not everybody was in on the answer on this one. So if you see something that you're not sure of or doesn't make sense, please don't hesitate to ask. Our job here is to convert 165 pounds to grams. So where we're going to start is with those 165 pounds. And I'll make my scaffolding. I better make this one longer. So I have 165 pounds, and I'm trying to turn this into grams. I kind of look at the fact that I've been given 1 kilogram is 2.2 pounds, and what this tells me is this unit fraction is going to take me from pounds to kilograms. That's not all the way to my answer, but it is closer. So, all right, I'll use that. And the way I'm going to use that is I'm going to put the 2.2 pounds on the bottom and the 1 kilogram on top. The reason I picked to put them there is because I want these pounds to cancel, so I need to put pounds on the bottom. Okay, got that. So far what I've done is gone from pounds to kilograms. Not quite done. Now I need to go to grams. And the way I'm going to get to grams is by using this unit fraction. 1,000 grams is 1 kilogram. I'll put my 1 kilogram on the bottom because I want it to cancel with this. So my 1,000 grams go on the top. Kilograms cancel. And the units I have left are grams. That's what I was trying to get to. So now I've used all the unit fractions I need to. The only thing left for me to do is multiply on top, multiply on the bottom, and then divide. So let's see, we'll multiply on the top. 165 times 1 times 1,000 is 165,000. On the bottom, I have 2.2 times 1, so that's just 2.2. And the only units that remain are grams. We'll divide by 2.2 and end up with 75,000 grams. So convert 165 pounds to grams, 75,000 grams. So if somebody weighs 165 pounds, then they weigh 75,000 grams. Any questions on that before we look at another dimensional analysis question? Outstanding. Very good. Okay, I think this is a pretty tough question. I'll be honest, it's not going to be a point of emphasis for us, but you may see it come up. So I want to make sure that you've at least had a chance to see us work through one. Use the fact that there are 5,280 feet in 1 mile to convert 38 miles per hour to feet per second. A lot of times in a physics class, speed will be given in feet per second. We don't use feet per second in day-to-day very often, but in a physics class, it would be certainly typical. miles per hour is more what we would be working with. The key here is the word per. And we've seen that before when we talked about unit pricing earlier. When we say per, that's an indicator that we need to divide. And so what our job to do here is convert 38 miles per hour into feet per second. So we're converting 38 miles per hour. So that's where we're going to start, is with 38 miles per hour. What's different about this one from the previous questions is now the units we were given right at the start have per involved. So we have units in the top and the bottom of the initial number that we're working with. What we're going to do is we're going to convert this till we end up with feet per second. We're going to end up with feet on the top and seconds on the bottom. So we have to convert not only what's in the numerator, but also what's in the denominator. One of the things we've got to do here is convert miles to feet. And I happen to have a unit fraction that's going to do that. There's 5,280 feet in 1 mile. So I'll put my 1 mile down here, my 5,280 feet in the numerator. Oops. At this point, my miles cancel. And if I were to quit right here, the units that I have are feet per hour. Well, it's not what I'm after, but it's closer. Feet per hour is closer than miles per hour. So now what I have to do, I'm done with the feet. That's where I want it to be. What I've got to do next is I've got to work on changing these hours to seconds. I don't know about you. I don't have any idea how many seconds there are in an hour. But a unit fraction that I could use could be the fact that there are 60 minutes in 1 hour. That I know. So I'll use that. 60 minutes in 1 hour. Hours in the bottom. So I'm going to put my 1 hour on the top and my 60 minutes on the bottom. Hours cancel. Okay, I'm not quite there yet. My units right now are feet per minute. If I were to quit here, I would have feet per minute. Well, it's not what I want, but I am closer than I was before. And now I get to another fact that I actually do know is that there are 60 seconds in 1 minute. And so I can use that as a unit fraction. 60 seconds is 1 minute. So what I'm going to do here is, let's see, I need to put my 1 minute in the top so that that'll cancel with the 1 minute that's in the bottom. And the 60 seconds goes on the bottom. Now the minutes cancel. And when I go back to look at my units, I have feet per second. That's what I was trying to get to. So now I know I'm done with all the unit fraction part of this problem. Now I'm to the place where I need to multiply across the top, multiply across the bottom, and then divide. So let's do that. 38 times 5,280 times 1 times 1. So this number by itself doesn't really mean a whole lot. It's 200,640. And then in the denominator, I have, let's see, 1 times 1 times 60 times 60. So 1 times 1 times 60 times 60 is 3,600. I need to divide those. So 200,640 divided by 3,600, and we get 55.733333. This we know now is in feet per second. And the last thing I'll do here is I was told to round to the nearest tenth. So we'll find the tenths place, look one space to the right, that's for lower. So we'll round this down to 55.7 feet per second. So if we're traveling 38 miles per hour, then we're going about 56 feet per second. I think that's a tough one because we're not only changing units in the numerator, but we're also changing units in the denominator to start with. But the philosophy doesn't change. We use a unit fraction to move the units along how we want them to move along. First, we went to feet. Then we turned our hours into minutes. Then we turned our minutes into seconds. Yeah, I agree. I agree, Nicole. And I will, like I said, you may see one of these along the way, but it won't be a major focus for us. Our kind of standard dimensional analysis question will look more like this one. That'll be the sort of the primary focus for us. One thing I wanted to point out is in your homework assignment for today, the problems from section 9.1, number 24 is not as difficult as it first appears. Don't try to force this one into some of the stuff that we've talked about today. Just use your problem solving skills on that one. I'll leave it like that. Just